Alright guys, welcome back. Today we're going to cover Unit 2, tutorial number 4, labeled Enzymes. Okay, so today we're going to talk about enzymes. And I'm on page 4, but let's just give an overall introduction to what enzymes are. Enzymes. They are proteins, so this is a type of protein, okay? And what they're going to do is they're going to speed up reactions. That's really their main job. That's pretty much all. Oh my gosh, reactions. Okay, so enzymes speed stuff up, and this is largely responsible for things like your fruit ripening. That is an enzyme which we'll talk about in unit 2, so I won't, auxins, gibberellins, all that kind of thing. We'll talk about all that in unit 2, so I'm not going to worry about ethylene and abscisic acid, all those kinds of things now, but they are they're meant to speed up reactions. They're meant to like ripen fruit. Or with like foods like meats, you can use in cooking. They use a lot of enzymes to break down certain things. So like heat denatures meat, right? So when you cook a meat, it changes color because you're breaking down all the proteins. Well, if you add things like garlic or lemon juice, lime juice, papaya, sometimes honey kind of works. It depends with the honey, but the idea is if you get these different things, they can actually add enzymes or catalyze the reaction. Remember, to speed up and sorry, this pen's pretty cool. It actually has like a light up feature. I don't really know why, but I don't know. It's cool. In any case, speed up. Another word for that is going to be catalyze. So you're going to hear me use that word a lot when talking about enzymes. Okay, speed up or catalyze. So anyway, when you add onions or garlic or lime, papaya, honey to a meat, it often helps soften that meat or helps it cook a little quicker. Okay, so that's all catalyzing the reaction. Um, but yeah, so that is an introduction to what enzymes are. So we're gonna go ahead and move on. Let's go ahead and go to page 5. Page 5. Okay. So enzymes work under conditions. So like all proteins do what they do, right? But enzymes require conditions. So they require certain things to happen, require conditions. And all this really means is that your fruit won't ripen if it's not time to ripen. Like there has to be something ready for that. Your body releases a hormone when you've eaten, right? So when your body releases that hormone, you feel full and that kind of thing. Enzymes can speed up that feeling full feeling. So, a lot of diet pills include enzymes or catalysts, which increase the amount of that hormone in your body, which reduces the amount of food that you want to eat, that kind of thing. So, it requires certain conditions to be met. There has to be like enough of something or too little of something before enzymes start just doing things. So your page 5 describes them as referees who regulate the game without playing in it. I don't know if I really like that analogy. What I would call enzymes is something closer to like a specialist. So you don't just go to a specialist for whatever. Like if you get a cut on your finger, you're probably just not going to go to a neurology specialist. It's not that big a deal. You're just going to get a band-aid or that kind of thing. Enzymes are specialists. So when certain conditions are met, so like when I have a neurological condition, I go see a neurologist or a brain doctor, right? Or if I have a heart condition, I go to a cardiologist, that kind of thing. So enzymes are like specialists. Electricity. You have general electricians, and then you have like power plant electricians. You don't go to power plant electricians if your lights won't turn on. That's just stupid. All right. So that is the general idea. I would call enzymes closer to specialists than I would to a referee. All right, specialists. So let's go ahead and move on to page 6. And one of these conditions, one of the most important ones, is activation energy. Okay, so I showed you guys a while back. Let me see if I can't pull those notes real quickly. So you guys might remember in our metabolism, the transforming energy part, I drew this right down there. So you'll notice that we have the energy of activation. Well, it's going to show up again here, okay? So keep this graph in mind just to, reference things back to what we've already talked about. But that activation energy is the energy required. So it's required to do something. All right, required to do something. Nope, something. I was supposed to say something. That's an S right there. I don't know why I did. Anyway, so this is your energy required to do something, okay? And this is for any reaction. So if I want to set something on fire, if I want to cook some meat, if I want to do this or that, I have to have a certain amount of activation energy. This is actually fairly easy because let's say you want to toast some bread, right? Well, to get that reaction to start, to toast some bread, you've got to have some heat. You can't just like sit the bread on this piece of paper and it'll heat up. It's not going to work like that. I have to, I have to heat it up a certain amount. Like I can't just put it on low heat on the stove or something like that. I'm gonna have to turn it up a little bit higher than that. Okay, so there's activation energy. What enzymes do is enzymes speed up reactions by lowering activation energy. Basically, they make it a lot easier to do things. Uh, all right, it's kind of like when you have a fire. I'm not gonna draw a fire right now, but if I had a fire, right, um, I could just keep adding wood to it and whatnot, but if I were to throw gasoline on it, that's a lot like this idea. It's a lot like lowering the activation energy. It just makes it a lot easier to start a fire if you have fuel to start it all up. Alright, so enzymes work in that same exact way. They just make it a lot easier to start doing what they want by lowering activation energy. So just this is another way of saying makes it easier to start. Okay, makes it easier to start. Because starting a reaction requires you to hit that energy of activation. Alright? Uh, and they gave you a graph in here, which is pretty nice. I'm gonna grab this graph from earlier that you guys just saw. I'm gonna add a line to it. So when you guys see, if any of you ask for these notes, you're gonna notice that it's gonna change a little bit. But remember, we have our energy of activation, and here's our reaction, right? This purple line is our regular reaction. Well, I'm gonna use this. Is this a different color? You guys even tell that's. You guys can tell that's a different color from the purple. So what happens is now my energy of activation is going to be significantly lower. So I might start in the same spot, but what's going to happen is I only need to get here now, and it's still going to reach that same level. So it just makes it a lot easier for my whole thing to happen. All right, makes it easier for my energy of activation to happen, and now my reaction is happening here. So instead of needing all 100 energy for activation, I'm gonna start at like I don't know 80ish. So it just makes it easier. All right, and the more enzymes you put in, the more catalysts you put in, the lower and lower this activation energy gets. But because it's lower and lower, it's a lot easier to start. Okay, so just remember, enzymes make it easier to start a reaction. All right, page 7. Uh, so page 7 has a question on it. It's pretty simple, pretty straightforward. Just remember, enzymes require or lower activation energy. Activation energy is just the energy that you need to go ahead and start a reaction of any kind. All right. Now they drew enzymes. Okay, I'm gonna draw enzymes a little bit differently. This was one of my areas in college, so I know quite a bit about enzymes. I know them like pretty detailed. I'm gonna try and keep it simpler just to make life easier because you guys really don't need to get into all the nitty gritty details. So we're gonna use a general idea. It's a lock and key idea. So here's your enzyme. Okay, your enzyme's just chilling. Uh, it's just chilling. Alright, and it doesn't do anything while it's just sitting around. This is called a biocatalyst, by the way. Biocatalysts are things that exist in your body, so they are biological. They are living, so just these things in your body, but they are catalysts, so they speed things up. But the reason they are biocatalysts is that they don't change. They just kind of chill out here and they look like this all the time until they're used. When they're used, there's going to be something over here that comes in. So like, here's my enzyme. So here's an enzyme. And then I'm going to get something that comes over here. So like here's a triangle hanging out here. And then here's another triangle hanging over here. And what's going to happen is that my enzyme is going to eventually, when I'm ready for it, so like let's say this was the enzyme for hunger and all that jazz. Or maybe it's making it easier to get full, right? So when I put in this enzyme, what's going to happen is that these little things called substrates are going to connect to my little guy. And maybe they'll connect one at a time. So like one of them moves down here, but this guy's still up here. He's just chilling. So next step, you're going to get another one. And what these are called, by the way, these little gaps that I keep fitting stuff in, these are called active sites. Basically, you can think of it as if you don't have anything attached to this, you are not active. All right. So now I'm going to have the other one join in as well. And now I've finished my puzzle piece. So once my puzzle piece is done, this is an activated enzyme. Okay? And they don't all have to have 2 spots. They can have a million spots. They can have 1 spot. You never really know. Enzymes just have varying amounts of spots. The idea is to get activated, they have to have certain things available. And if these certain things are not available, I cannot use it. So if I only had one of these triangles over here like this guy will never be active. I have to have 2 of them in existence or else it will not work. Alright, so you start off, just with your enzyme chilling. It's called a biocatalyst, and you're just going to keep moving on, and eventually everything will connect, and now you'll have an activated enzyme. But that is the idea. Those are the 3 main words that you have to understand. So enzymes, substrates, and active sites. Okay? Now, there are a lot of different ideas on how these kind of blend together. I gave you guys more of like a puzzle or a lock and key method. There are a couple others. I don't know if they're going to talk about all the different ways to think about them. So let me wait until my page loads real quick. In any case, while that's loading, yeah, there are a bunch of other ones. It doesn't look like they're going to describe them to you, so I'm not going to either. Just keep in mind, this will work for now. This is a very fairly good understanding, so I want you guys to go ahead and go with it. So let me get this entire page on screen temporarily, and yeah, so my page is loaded now. And it talks about how you're breaking down food. This is actually kind of good, so I'm going to go through page 9, but in a much simpler way. All right, so you're going to eat some rice. All right, and rice has a lot of starch in it, so rice is very starchy, and that's why when you clean rice, you get all that milky water. That's all the starch that you're washing off, but it still has a bunch of starch in it as well. Starch is one of those macromolecules. So, 1 sec. Starch is going to be one of those macromolecules that are shaped like this. You guys have seen it before. I've drawn it with all these little hexagons. Oh my god. Well, that was an awful hexagon. But you guys remember that I chained together a bunch of these things? Starch is going to be, if I'm not mistaken, I think it's like 3 of these things. I'm going to draw 3. I'm pretty sure starch is 3. I'll Google it in just a sec. Give me 1 sec to make sure about that. Yeah. So looking up starch. Starch is C6H10O5. Yeah. So it's definitely 3 of them. Okay. So you've got 3 of these little chains here. That means that this is, if you guys happen to remember, this is a tri or a polysaccharide. All right. Saccharide. So remember, these are sugars or saccharides, carbohydrates, whatever you want to call it. But this is what starch is. Starch is a tri or polysaccharide. All right, there are 3 parts. So this can be broken down, and if we break it down into simple sugars, we're going to get the energy from the bonds. Right, can be broken down for energy. All right, so this is absolutely important for you guys to remember. Is just you break these things down for this. Now, to speed that up, you have something called, oh my god, I keep forgetting about this one. I need to quit clicking it. It's very cool, but kind of annoying. But you have something called amylase. All right. So amylase is an enzyme. It's a very specific kind of enzyme. And what it's going to do is it's just going to catalyze a reaction. All right. It catalyzes. And what that means is it speeds up. So it speeds up the process of breaking down starch. Breaking down starch. Okay, so it makes breaking it down easier. It makes this 3 thing. It essentially makes these bonds a little softer, so we can break them over and over and over a lot quicker, and you'll end up with just glucose. You'll end up with just 3 separate things. So instead of being bonded together, you just got 3 separate things, and you've harvested the energy from them. These are a lot easier to deal with. Okay, so this is what you end up with because of this amylase here. Yeah, so the rest of this process is all pretty straightforward. They're not really talking about anything fancy. I just wanted you guys to understand another example, and eating food is probably a pretty good example, The idea is, again, you start off with something complex and you're just trying to break it down for energy. It's food, it's rice in this case. Could be anything starchy. So you could have thought about this as bread too. So amylase is also like that. But keep in mind, I told you guys that saccharides or carbohydrates are also called sugars. So when you break these down for energy and all that, you break them down into sugars. You break them down into glucose. So each of these is a glucose. Glucose. All right, but this whole thing up here, this was a starch. So I said rice earlier, but let's say you took a piece of like white bread. So white bread is very, very easy to break down. What you can do is you can just take white bread, you put it on your tongue, and your tongue will release your obviously saliva, but in there is amylase and whatnot. And the amylase will break down your starches, so it'll catalyze your starches. And what's going to happen is it's going to catalyze that breaking down process, and you're going to end up with glucose. Glucose, I told you earlier, was sugar. So that's why when you put white bread on your tongue, you just leave it there for a while, and it starts to taste a little bit sweet. And now, for some people, this takes longer than others, so if you're going to try this at home, give it like 5-10 minutes. It might take a bit. But in any case, you can actually see that for yourself. Okay, so what we've got now is on page 10, they did talk about one of these models. It's going to be called the induced fit model. So earlier I showed you guys this like lock and key model, right? So the induced model is something like this. So I have an enzyme that looks like, I don't know, like that. Looks like, kind of like a moon. Okay? And obviously this is like a ball-like shape that's going to fit in here. So this is your enzyme. All right? And then you're going to have a substrate. So a substrate. And your substrate is going to be this circle. So this would fit perfectly in there. But you'll notice that I can't just shove it in there because it has this like entry area. So this, remember, this is your active site. And this entry area is hard to enter. I just realized that on camera that looks kind of bunched together. I should have definitely separated these. So I'm going to redraw these real quickly. Something like that, sort of. And then we had our substrate, something else over here. So this is a substrate, and this is our enzyme. And then don't forget, of course, your active site. All right, so that's that little hole in the middle of all of that. So the idea is this. This is the induced fit model, induced fit. So when all of your conditions are met, and remember, our enzymes do require conditions, whatever they might be. In the situation with the rice, you obviously have to have rice in your body. In the situation with the bread, you obviously have to have bread in your, in your stomach or in your mouth, that kind of thing. But they're not going to happen if you don't have any bread. Like your enzymes aren't just constantly breaking down your tongue for sugars because that would be pointless. So the induced fit model says that once all of the conditions are met, once you have both your enzyme and your required substrate, what's going to happen is that the enzyme can actually open up a bit. So instead of being like that, it can like stretch out like this. And then the little ball can go in here. All right. So now you're going to end up with something like, now it's open, right, that-ish. And there's going to be a ball in here. It doesn't quite fit properly, but what's going to happen is your induced fit means that this thing will curl back around that substrate. Alright, so now there's a substrate in there. There you go. So it's filled. Right? Oh, you guys can't really. There you go. So yeah, it starts here. You have a substrate, you have an enzyme, so it's all ready. Everything's ready for this induced fit. So it'll open itself up. So it was tightly closed. It's going to open up, and that thing's going to go in the middle, and then it's going to close back around. All right. So the idea of induced fit is that you're going to start with one shape. You're going to open up a little tiny bit. Okay, open up just a little bit, and then you're going to take in this substrate and then close back on the substrate. But the idea is that this enzyme will change shape temporarily, but it will always go back to its original. Okay, so this is an induced fit model. That one is actually what I'm more used to. I see a lot more of the induced fit model. Very rarely do you find enzymes that are actually just cookie cutter lock and key types. Like these exist. There's no doubt that they exist. It's just that they're a lot harder to find and they're not as useful. These are much, much more common. Okay, you can think of the induced fit model kind of like a Pac-Man, and you can think of this as like a lock and key. So this is just, you can't change the lock, you can't change a key, you just got to put the right key in the right lock, right? With this one here, it's still the right key, right lock, and all that jazz, but this would be like a lock that has some kind of weird protection. So it's a lot easier to say this is more like a pack. All right, let's go to page 12. Nope, just kidding. Oh, actually, yeah, that'll work. So page 12 goes over this entire process, which I don't really know how much you guys need to know. Feel free to run through the exercise on page 12, but we've already talked about how all of this works, so it actually looks a lot like what I just did earlier. Yeah, so you guys have actually already seen most of this, page 12, because page 12 kind of does what I did here. For the most part, it mixes like this diagram alongside that diagram there, sort of, and this one, sort of. It kind of mixes all my diagrams together, so we've already gone over it, so you don't need to stress it, but if that didn't make sense to you, feel free to take a look at page 12, all right? Proteins. So now they're talking about proteins and how they're designed. So remember, enzymes are a type of protein. Proteins are just a more generalized form. It's kind of like saying, chicken nuggets are a type of chicken. They are chicken and all that jazz. So enzymes are proteins and all that jazz, but you just don't call them just chicken. I'm having chicken nuggets, right? So anyway, proteins. Let's go ahead and break these down, which is actually something that we do. There are going to be 4 levels of proteins. So 1, 2, 3, 4. And I think we talked about this back when I was talking about macromolecules, but I'm going to talk about them again. There's primary, secondary, tertiary. Remember, tertiary means 3, so it's the 3rd level. And quaternary. Remember, quaternary means 4. All right, so you have your primary, secondary, tertiary, quaternary. And remember, this one's a chain of amino acids, right? So amino acids like that. Secondary is going to be that pleated thing, so that folded or pleated shape. And I had trouble drawing this last time too, but the idea is that it was folded and it's a 2D figure, right? It's a bunch of squares. It's just kind of folded up together. I showed you guys an example of that. Tertiary is like a shoelace, all right? And then quaternary is like a whole lot of shoelaces. I'm not going to go through all the trouble to like draw a bunch of shoelaces, but you get the idea. This is a lot of shoelaces, okay? So those are our 4 different levels. And what happens with these proteins is that they denature in heat or in enzymes or in certain pHs, that kind of thing. And denaturing just means to break down. So if I have this kind, it will break down all the way down to this primary version if you have the right things. I don't really know what page 14 and 13 will do for you. Or 15. So these talk about the breakdown of proteins. It really doesn't matter. You just have to know that you find proteins in all sorts of levels. So you might find one in secondary. This one can absolutely be broken down. It's easier to break down, obviously. So to get from here to here is obviously a little harder. But to get from secondary to primary, super easy. Tertiary to secondary, easy, that kind of thing. All right. So the idea is just proteins break down every once in a while. 16. So they're going to talk about factors that affect enzyme action, okay? So enzymes work under different conditions, like we talked about earlier. Some of those conditions include temperature, so let me go back. No, let's just start a new conditions page. So we have new conditions. One of these conditions is temperature. All right, you have to have certain temperatures for certain reactions. For example, it's really, really hard to get the reaction of lighting a match to work if it's windy or that kind of thing, or if there's no oxygen in the air. So that kind of thing. Certain things rust easier in warm weather than they do cool weather, that kind of thing. So temperature absolutely matters. pH is a big deal. Substrate existence. So if you don't have any substrate, obviously you can't do it. But all sorts of conditions like that. And let's see. So they talk about how every enzyme works best within a certain pH. That's absolutely true. Do keep that in mind. All right. For example, if you have a change in, they give you pepsin and whatnot, and that works in your stomach and that kind of thing. So when you digest food, your body sits at a certain pH. All right. But unfortunately, if you were to change that, your pepsin and whatnot would no longer be active, so you wouldn't be able to digest food properly. So it's really important for your body to maintain a certain pH level. That's why if you drink water that has a ridiculously high or ridiculously low pH, your body actually ends up suffering from that. So you want to sit on, and it's actually on a slightly basic, slightly alkalinic side of water. So instead of being 7 exactly, it's like 7.2 or something like that. But the idea is you want to keep it around that area. So if you're drinking water with an acidity of like 3, you're probably in trouble. That's probably why you're dying and that kind of thing. All right, so if you change the pH in the body, it will deactivate and denature the enzymes so they don't work anymore. All right, temperature, we just talked about it. For the most part, by the way, most reactions happen better in higher temperatures. For the most part, things are faster when they're warmer. Let's see. And then it talks about substrate concentration or saturation. Okay, so keep in mind, saturated just means filled up, right? So what can happen is that saturated means filled up. In those examples earlier, I kept showing you the shape, right? So this enzyme and whatnot, it's something like that. So if I have, a bunch of substrates, whatever, there's gonna get to a point where I just can't use any more of this. So like you can put as much substrate as you want. So these are like the ingredients. These are one of the conditions, right? With temperature, there's an optimal condition. You can be at a certain temperature, you can be at a certain pH, you can be at a certain substrate level. If you end up with too many of these substrates, your reaction is not going to go any faster. So on page 18, they have this wonderful graph that shows, all right, so here's how fast your reaction is, fast reaction. The higher up it goes, the faster it is, right? And then this is how much substrate you have. Substrate. It's just all those little things, right? You're gonna reach a point to where eventually you're gonna be like, oh great, my reaction's moving awesome, super super fast here, right? But if you keep adding stuff, it'll just level out. You'll notice that it doesn't speed it up anymore, so you'll just be wasting stuff. It's kind of like a sponge, so like this thing, it can't hold that many substrates. It can only hold 2 of these things, so the extra 3 are just completely wasted. So you don't want to do that kind of thing. All right. Let's take a look at page 19. We already talked about denaturation on 19, so I talked to you about how it needs to break down from higher levels to lower levels. So denaturation is just breaking down all of these things, temperature and pH, and technically substrate, but mostly temperature and pH. If you have it at the wrong temperature or at the wrong pH, your body can stop working properly. So I told you earlier, if you had that pepsin in your stomach and you change your body to have a way lower pH, it's going to ruin the pepsin and you wouldn't be able to digest food properly. I'm sorry. If you were to drink really basic things, it would ruin the pH here. That's what it was. All right. So let's go to page 20. They're just asking a question. 21. Okay. So we're back to the summary. So what I want to do is I want to just review and summarize everything real quickly again. Remember that you can mess up enzymes if you change pH or temperature. Alright, so if you change your pH or temperature, just assume that your enzyme's going to get messed up. It's either going to get denatured or it's going to become useless. It's not going to be able to do anything. It's not going to be able to function properly. Because what it'll do is it'll change its shape. I told you earlier that we have like the induced fit model where the enzymes naturally change shape. Well, if you were to add a brand new pH, or maybe you're just heating everything up. So this thing was a little like weird moon-shaped crescent looking thing. What you could do is you could end up making the enzyme be a giant squiggly like this. In which case now that active site, that circular substrate, is no longer going to fit in this thing to where it's useful. So it becomes a useless enzyme. So that's essentially what denaturation is and whatnot. We talked about what an active site is. So active site is where the substrate fits into the enzyme and then activates the enzyme. Let's see, change in pH. I think that's it, honestly. So just, looking over everything again, I'm going to go through them page by page just so you guys have them. Feel free to pause. Or if not, this is the end of the video, by the way. I'm just putting everything on screen one more time just in case you need it. So there is page 1. All right. And page 2, lower just a little bit, and then there you go, pause, and then page 3. Alright, so these are the notes. Feel free to let me know if you have any questions. I think this will cover it. This mastery test is going to be hard, though. It's going to be kind of heavily worded. You're really going to have to understand things in order to get through this one, but let me know if you have any trouble, okay, guys? Good luck, and I'll see you guys next video.